All right, today we're going to dive into a little organic chemistry and meet one of the most important families of molecules out there. Seriously, they're behind the smells, the tastes, and even a lot of the materials that literally shape our world. So let me ask you this. What do you think connects the warm, spicy scent of cinnamon to the sharp sting of vinegar? It sounds kind of weird, right? I mean, they couldn't be more different. But what if I told you they're actually related? Like surprisingly close relatives on the same chemical family tree. Let's find out how that's even possible. Okay, so here's our game plan. First, we'll look at the common ancestor that links everyone together. Then we'll meet the two main siblings, the aldehydes and ketones. After that, we'll get introduced to their acidic cousin. And finally, we'll see how this whole family shows up in your day-to-day life. Every great family has an origin story, right? A common ancestor where it all begins. Well, for this chemical dynasty, it all starts with one simple but incredibly powerful arrangement of atoms. Say hello to the Carbonyl Group. This right here, this is the whole deal. A carbon atom double bonded to an oxygen atom. This C double bondo is the heart of every single molecule we're talking about today. If you remember one thing, remember this. It's the family signature. So why is this little group such a big deal? Well, it all comes down to polarity. You see, that oxygen atom is an electron hog. It pulls the electrons in that double bond towards itself, which leaves the carbon atom a little bit positive. And that turns the carbon into a prime target for chemical reactions. It's what gives this entire family its very, let's call it, outgoing personality. All right, so we've met the ancestor. Now it's time to meet the first major branch of the family, the first sibling in our story, the aldehydes. So, what makes an aldehyde an aldehyde? Look closely. You see our familiar carbonyl group, but on one side it's always bonded to at least one hydrogen atom. That little H is its defining feature. Think of it like a birthmark that tells you exactly who you're looking at. And the consequence of having that hydrogen is just huge. Because hydrogen can only form one bond, the entire aldehyde group has to be at the very end of a carbon chain. It can't be sandwiched in the middle. It's a terminal group, always on the edge. Okay, let's move on to the other sibling. If aldehydes are always at the end of the line, their sibling, the ketones, love to be right in the middle of the action. And here it is, the key difference. On the left, you've got the aldehyde, with its signature hydrogen atom stuck at the end. But over on the right, the ketone's carbonyl carbon is bonded to two other carbon groups, no hydrogens directly attached. That tiny structural difference, it means everything. And that's really the big takeaway here. Aldehyde on the end, ketone in the middle. This seemingly small difference in location completely changes their chemical properties, their reactivity, and how they behave out in the world. It's all about location, location, location. Now that we know the two main siblings, let's meet a really important cousin, the carboxylic acid. And as the name implies, this one, well, it has a bit of a sharp, acidic personality. So how do you build this cousin? You take our ancestral carbonyl group, and instead of attaching just a hydrogen or another carbon, you attach a hydroxyl group. That's an OH. That combination of a carbonyl and a hydroxyl on the very same carbon is what creates a carboxylic acid. So why is it acidic? Okay, this is a fantastic little chain reaction. The carbonyl oxygen pulls electrons away from the carbon. That carbon, now feeling a bit electron poor, starts pulling electrons from the oxygen of the neighboring OH group. This whole tug-of-war weakens the bond to that final hydrogen, making it super easy for it to just pop off as a proton. And releasing protons, well, that is the very definition of an acid. Okay, so we've met the main family members. We've seen their structures. Now for the best part. The family reunion, where we see how all these abstract molecules actually show up in our world. And here they are. That amazing, unique smell of vanilla, that's an aldehyde. The nail polish remover under your sink, that's acetone, a classic ketone. And the sharp, sour sting of vinegar, that's acetic acid, our carboxylic acid cousin. And hey, remember our opening question? The scent of cinnamon comes from an aldehyde, and the sting of vinegar is a carboxylic acid. They're all related through that core carbonyl group. Now, get ready for this, because this isn't just a few niche examples. Over 90%, more than 90% of the compounds that create the flavors and fragrances we experience every single day are built on either an aldehyde or a ketone structure. 90%. So let's just put it all together. Aldehydes, they often give us those pungent, sweet smells. Ketones are key to a lot of solvents and sweet tastes, like the sugar in fruit. And carboxylic acids, well, they are the undisputed kings of sour and sharp tastes. And that's what's so incredible. From one simple, elegant structure, that carbonyl group, an entire family tree blossoms. A family that's responsible for so much of the sensory world we live in, from the sweetest perfumes to the sourest candies. It's a family that's absolutely fundamental to nature and to industry. It builds our foods, our medicines, our materials, which really leads to the final question. Knowing the power and the versatility of this one chemical family, what will we build with it next?